So welcome back. Last Monday, we looked at examples which are relevant for both the exercise solutions, but also relevant for the coming discussions. Now, we were looking at this slightly boring topic of a falling object. We are going to, in homework number 3 and also in homework number 4, we are going to add more complicated forces to it so we can make a more realistic model for the motion of such a falling object in 2 dimensions, if we want to do that. Now, the topic today is actually to give you some further examples on forces which we are going to encounter again and again in this course. And in addition, how we would solve these. And we're also going to look at some of the exercises for the coming homework, which is exercise 5 and exercise 6. So we will discuss these topics a little bit today as well. We may, since we have a new topic which deals with the energy and work theorem, we may skip that so that we just dedicated all of Friday to exercise solutions. So today, unfortunately, we have to run this through Zoom, and I will update you if we may have to run things through Zoom on next Monday. But on Friday, Shuju and Abby will be present in STEM building, so you can come physically, and I will discuss with those of you who only can connect online. Okay, so the topic today is to look at further examples, but we're also going to repeat some of the results which we obtained on Monday. And I also wanted to use this occasion to give you a quick reminder of some small things. Now, I've been asked about something like an honors option, and this is fully possible with classical mechanics. And if you go into the main GitHub address, so this allows me to indicate you where we have possible honors projects. So I have listed a series of projects which people have looked at in the previous years. So there is anything from solving differential equations in classical mechanics with machine learning to study the chaotic pendulum or other types of projects. So if you're interested, Michigan State University has this possibility of the honors projects from the Honors College. And the honors project is something you would enlist on. You go to the honors option, you just search for that one through the Honors College, and then you have to submit a form, and I will receive an email, and then I will just, depending on what kind of things you want to do, I will just approve the project, and that will give you some additional possibilities to study and to deepen your interest in, let's say, a physics problem here. So that's just one thing to think of. The other thing, which I simply want to do now, is also to remind you, in addition to the lecture videos and so on, I do also place the handwritten notes, which we produce every lecture under this folder. So for this time is the spring 23, and the from Monday you will find this handwritten notes here, and I just wanted to use that one to remind you quickly of what we did on Monday. So Monday was us studying this falling object in 2 dimensions. We started with a 1-dimensional, and then we went into 2 dimensions with and without a model for air resistance. And in this specific case, what we did now was to add air resistance in one direction. And depending on what kind of type of air resistance we have and the velocity of the object which is falling, you can deduce an experimental behavior which goes either like the velocity squared or just as a function of the velocity. Now, there's a reason why I wanted to bring this up, because it allows me to emphasize the ways which we are solving these type of problems. So the standard way is simply now to, if you start with a model for the acceleration, so this is the acceleration which we have here, we have the total forces, and then we divide by mass, we have the acceleration, and then we can integrate up again, and we end up with an equation here for the velocity with respect to time, the derivative, and we can then integrate up this equation by just standard integration techniques. So this is one of the ways by which we would typically solve this type of equations. And the other approach which we can do then is to solve these equations as differential equations, as we will point to today. But the basic recipe, when we now do this, if we can integrate, this is the simplest possible way, and this is what we did on Monday. So we integrated up, and then we found an analytical expression for the velocity. And then you can integrate up again, and then you get an analytical expression, in this case, for the position as well. And what we did as well was to also look at the same problem in 2 dimensions. And in 2 dimensions, we need to take into account the velocity vector. And in 2 dimensions, this is a model which now has the velocity times the absolute value of the velocity. So when we then looked at the equations, and we want to look at this from a differential equation point of view. So the previous case, which you saw here, what we did was just to integrate, starting from the acceleration. We integrate up and we find the velocity, and we integrate up and we find the position. Now, what we did next was actually to look at these equations from a differential equation point of view. So what we did, we have the velocity in the x and the y direction, and we rewrote the whole problem as a set of coupled differential equations. Now, the problem then gives us, since this is a problem in 2 dimensions, we get 4 coupled differential equations. And in some cases, we can actually solve these equations analytically. So in this type of recipe, you would try to solve the differential equations, which in principle also means to integrate up and find the solution. So for this particular case, when we now rewrite the equations, what we end up with is a set of equations which we cannot solve analytically. And the reason for that is that the equation for v of x depends also on the unknown v of y. So v of x is an unknown, v of y is an unknown, and we would call these for coupled differential equations. And we are going to meet another such example today. So this is the kind of equations where we are trying to solve the differential equations, but we have to recur to a numerical solution. So when you cannot separate equations, that may be an indication that you cannot find an analytical solution. It doesn't mean that you cannot find it, but it's normally a clear indication that with the coordinates we have chosen and the degrees of freedom, x and y, we will not be able to find an analytical solution if we insist on those degrees of freedom. So this is actually one of our first encounter of coupled differential equations where we have to revert to a numerical effort. We are coming back to this. So the other case which we looked at was a case where now the object is falling slowly, and then we can assume that this air resistance can be modeled as a function of just velocity. And when we do that, we end up with an equation which we could just integrate up again as we did before. So we have the acceleration in the x direction, and then we would have the acceleration in the y direction, and then we would simply integrate up acceleration in the 2 directions as we did last time, and then we would find an analytical expression for the velocity in the x direction, and similarly we would find an analytical expression for the velocity in the y direction. So with the velocity in the x direction, we can integrate up, and we have the equations for the position as a function of time. And similarly, we would do the same with velocity. So these are things which you will practice a little bit in the present homework. Now, what I want to do now today is to present you with some other examples, and then we are going to look at the exercises for the coming homework. And these are, I will in particular look at exercise 5 and also exercise 6, and then just see how far we get. Okay, so this was a little bit a kind of recap of what we did on on Monday. So let's now switch back to the whiteboard and just take a look at some other examples of forces which we have encountered before, and see how we can actually rewrite these as partial or a couple differential equations. So let's just bring up the whiteboard here. Here we are. And let me know if there are any problems, any questions to these type of problems which we have been looking at. So unless there are any questions, the next problem which we are going, next example which we're going to look at is the gravitational force acting between the sun and the earth. So this is going to be example 3. And in this particular case, we do now have a force which is acting on the earth from the sun. And if we follow Newton's law, if we look at the force which acts on the sun from the earth, it has just the opposite sign. So that would be Newton's third law. But let's now assume that this is given by minus g. This is the gravitational constant. This is the mass of the sun. And this is the mass of the earth. So the mass of the sun has this specific symbol. For those of you who are familiar with astrophysics or astronomy, you may have encountered that type of symbol. Now, since we now are dealing with this object in suppose 3 dimensions or 2 dimensions, we need to introduce a vector sign. So since we have the vector here, we're actually going to have a force which now depends on the absolute value of the distance between the earth and the sun. So this r is actually the distance between the earth and the sun. So this is actually cubed. And this quantity r is now given. So r is actually given by the absolute value of the distance between the earth and the sun. And if we're now just staying with 2 dimensions, this would be x squared plus y squared. And we are going to encounter this problem in one of the homeworks pretty soon. And then finally, in the second midterm, we're actually going to look at the numerical solutions of these equations for all the planets of the solar system. Now, this force is something which, when you then take away the r vector and divide by one of the r's from the denominator, then you have a force which is proportional with the inverse squared distance between the 2 objects. And now what we could do now, when we set up a coordinate system here, is the following. So you could now think of having a 2-dimensional coordinate system, and we would have the sun here, and then we would have the earth here, and this would be the distance from the earth to the sun in this coordinate system. And we have r here, we have a theta here, and in our specific case, what we get then is obviously that x is equal to r times cosine theta, and y is equal to r times sine theta. Now, the distance between the earth and the sun defines a unit, which is called an astronomical unit. And we are coming back to that one a little bit later. So just be patient. And somebody of you may actually remember the size of that unit or the magnitude of that unit. Does anyone remember this distance? You can write it in the chat, or you can just unmute yourself if you want. So I'm not expecting that you remember all the many of these physical units, but some of you may have actually seen the unit which is called the 1 astronomical unit. But if you don't remember it, I'm just going to write it down here. Oh, here we have the answers, eh? Fantastic. I love it. Fantastic. Thanks, folks. So if I rewrite what you wrote in terms of the kind of scientific notation, this is 10 to the 11th meters. Perfect. Thanks, folks. And then some of you may even remember the mass of the Earth, right? And the mass of the sun. Does anyone remember the size of the mass of the sun? It's just a curiosity from my side. Hey, I love this. Fantastic. This is 2 times 10 to the 30th kilograms. Does anyone remember the mass of the Earth? So let's just put that one in as well. Wow, wow. This is amazing. Thanks. This is 10 to the 24 kilograms. Now, you see now that the Earth is actually 6 orders of magnitude lighter than the Sun, which often means that when we make a model for the system, we are going to treat the Sun as a mass center because it's much more massive. And when we are going to model the solar system, you will actually see that this is a pretty good approximation. So you could think of the Sun as defining the origin when we want to model a system like the Sun and the Earth, because the Earth is so much lighter. And then we could just think of the Sun as defining a massive mass center, because we have 6 orders of magnitude of difference in mass here. But if we now go back to the technicalities here, what we could say now, since we have defined R in terms of this angle theta, we see now that we can replace R times cosine theta with X here. So that means that if we look at this expression here, we can define an X component and a Y component for the force by simply using the relation we have for X and Y in terms of cosine theta and sine theta. So that means that we could actually rewrite f of x as a minus g multiplied with the mass of this Sun, the mass of the Earth, and then we would have x, because this is the cosine component, and then we would have this divided by r cubed, which is now, and remember now that r is actually the square root of x squared plus y squared. And then we would have f of y, which is now equal to minus g times m times the mass of the Earth multiplied with y divided by r cubed again. Now, what we would do next is simply to find the acceleration. And this is the acceleration of the Earth when we keep the Sun at rest. So what we would get then would be something like f of x divided by the mass of the Earth. And that gives us the acceleration, a of x. And we would get minus g times m. And then we would have x divided by r cubed. And this is again the same as dvx and dt. And if we rewrite it, so let's just rewrite it in the full expression for r cubed. So we would have times x divided by, and then we have x squared plus y squared, and then cubed. So that's the expression which we are going to try to solve now. Then we would have a similar expression for the y component. So we would get an f of y divided by the mass of the Earth. And this is a of y. And if we do the algebra again, this gives us g of m times y. And again, we would get x squared plus y squared. And this is cubed again. And this is equal to dvy of dt. Then when we have these expressions, what we could do next is actually to put up that the velocity v of x is equal to dx dt, and v of y is equal to dy dt. And again, what you see is that we have, if we want to single this out, we have 1 differential equation, 2 differential equations, 3 differential equations, and 4 differential equations. If we had looked at this problem in 3 dimensions, we would have gotten 6 coupled differential equations. Now, if you remember back to the case we had last Monday, and which we repeated now right before the lecture here, when we looked at this object, this falling object with an air resistance which went like the velocity squared, then we said that the equations are coupled in the x and the y direction, and we see that we have the same thing here. So we actually have in the equation for the velocity in the x direction, we have a dependence on the unknown quantity y in the x direction. And similarly, in the y direction, we also have a dependence on an unknown quantity. So this could actually indicate that this equation cannot be solved analytically. It actually can. So when I on Monday said that if you see coupled differential equations, in general, you may not find an analytical solution, but this is a case if we now make a change to polar coordinates in 2 dimensions, or if we change to spherical coordinates, if we're dealing with a 3-dimensional problem, we can actually solve these equations analytically. And we are going to see that when we are getting close to spring break or right after spring break, that these equations for the Earth-Sun case can be solved analytically. And that allows us to make very nice, lots of nice, deeper understandings about things like the perihelion, the aphelion, which are typically the distances, the shortest and the longest distance between the Earth and the Sun, and many other things, and also why we get elliptical orbits. But just stay tuned. This is going to be fun when we get a little bit later in this, a little bit later during this course here. So this just stops here because if we want to move on, we would have to bring up all this machinery. But this is just to show you how we can set up the problem in terms of differential equations. So in the previous case, we could integrate easily. In this case, we cannot integrate easily. And we would typically then solve these as coupled differential equations. And if we cannot solve it analytically, we have to resort to the third type of approach, which is numerical solution. So let me just summarize that a little bit. So we have the first approach. That is simply integrate analytically. And we would then have an equation for the acceleration. So we would typically start with dv, and now I'm skipping x and y and c dependencies. And we would simply have dv equal to a velocity, which then could depend on time or may not depend on time. And then we would just integrate that equation there. So the typical approach then is simply to rewrite this as a dv of a times t multiplied with dt. And to get the velocity, then we get an integral where we integrate from v0 up to v, and then we have a dv here. And this could now be equal to an integral where we integrate from a time t0 to time t, and then we have our at prime and dt prime. That's the simplest possible way we can proceed. And then with that, we would get the position when we integrate the velocity. The second approach is then to solve coupled differential equations. And I know that not all of you are familiar with differential equations, but typically what we would do then, if we have a well-defined force, we have a dv dt equal to a. We started from a acceleration, which is given by dx dt, and I'm just simplifying everything to 1 dimension. And we would rewrite that in terms of 2 coupled first-order differential equations. And then we have 1 for position and 1 for velocity, like this. So 1 derivative for position and 1 derivative of velocity. And then we would solve this as coupled differential equations. The other approach, which is the one we often end up with because we cannot solve things analytically, is simply to solve 2. So that means the previous case numerically. And we are going to use all these 3 approaches in different ways. So sometimes we can calculate analytically, sometimes we can have to solve a differential equation, and at the end, in most cases, we actually have to do a numerical solution. So we started with the Earth-Sun case, so where we had a simple model for the force here. So let's look at a further example, which we're also going to study in quite some detail. So let's call this example 4. And please feel free to ask questions if something is unclear here. Now, this is a problem which I'm now just sketching as a one-dimensional problem, but there is nothing which hinders us to actually rewrite this as a two-dimensional or three-dimensional problem. And this is also the not too exciting case of a block sliding on a floor, on a surface. And this is fastened with a spring. And in this case, we have a velocity. It could go inwards or it could go outwards. It will have an equilibrium position, and it may have a position where we really stretch it out and where this kind of approximation, which we are setting up now, is not valid anymore. So this typical force here, if we now reduce this to a one-dimensional problem, this force is something which is going to depend on x, the position. So we have x here, the velocity, and time. And when we come to what is called harmonic oscillations, we are going to derive this force from a Taylor approximation of the potential which acts on an object. So now I'm just stating what the force looks like. So we can actually show that this force, which is acting from the, so you have the force which acts on this block from the spring. That is obviously the opposite, using Newton's third law, from the force which acts on the spring from the block. So they would just have opposite signs. And this force is equal to a minus a constant times the displacement. We can always rewrite this displacement in terms of an origin, but now I fix the origin to 0. So we are going to later, when we come to harmonic oscillation, so this will be in roughly 3 weeks from now, we are going to derive this force. And this force is actually something which is based on an approximation. It is not a fundamental force. The gravitational force, which we put up earlier, is a fundamental force, what we would call a law of nature. This force is an approximation which we make due to a Taylor approximation, looking at oscillations around an equilibrium position. We are coming back to that. So I'm just anticipating some results here. Now, this means that what we have now is that we have an m, if we stay just in one dimension, m dx dt, and this is equal to minus k times x. And then we can rewrite this in terms of initial conditions. We can reformulate the problem. So we will define an initial position, x0. We will define a v0 here. And we can now divide away the mass. So we can rewrite the equation dx dt, second derivative, is minus k divided by m times x. And it's common to actually define a constant, which is called a natural frequency. Actually, this constant has dimension frequency, which is 1 over time. And it's easy to see that when you look at when you perform a dimensional analysis of the differential equation. So we are going to introduce a frequency, which I'm just going to call omega 0. And it's called natural because it's defined in terms of the physical constants of the systems, which is given by this spring constant, which is a material-dependent quantity, and divided by the mass. So natural frequency or natural quantity means often that it's determined by the physical parameters of the system. So if we do that, we can rewrite the equation dx dt in terms of minus omega squared multiplied with x. And then we would rewrite this as two coupled differential equations. So we would rewrite it in terms of a dv, which is the acceleration, of dt. So this is a, the acceleration. And this is now equal to minus wx. And the next equation, which is simply dx dt is equal to v here. Now, this is also a famous differential equation in mathematics and in physics, obviously. So when you see an equation like this one, probably some of you have already seen the solution to this differential equation. Has any one of you seen it? And if you've seen it, what should the solution of X look like? If you've seen that. So this differential equation is a famous equation which appears in science. And you're going to encounter this equation again and again and again in different disguises. Whether you do electromagnetism, you're studying electric circuits, or even if you're doing quantum mechanics, you will actually see a differential equation which looks like that when you scale away all the physical parameters, and you're going to get something which is given in terms of periodic functions. Has anyone seen what kind of solution you can get for this equation? You may have seen it. Feel free to punch that in the chat or unmute yourself if you want to. If you haven't seen it, I mean, obviously you haven't seen it, but this is a typical differential equation which appears in science. And when we come to harmonic oscillations, you're going to encounter this problem again and again. So in just a few weeks, we are going to study this in more detail. But this is a case, a problem. This differential equation has an analytical solution, which is going to go like a cosine of omega times time, plus another constant. So B and A are constants, and we have sine of omega of t. So what you did in the first homework with cosines and sines is something which we're going to meet again in just some few moments here. So when you encounter a differential equation like this, the solution to that is given in terms of cosines and sines, which we then can rewrite in terms of exponentials. So it's a so-called periodic problem. And if you think of this block, which is oscillating back and forth, if we don't have any friction, it will just oscillate back and forth in a periodic way. It just comes to an end point and then goes back to the starting point, end point, starting point, back and forth. Very exciting, by the way. Any questions so far, folks? So I'm just presenting to you examples of physics problems which we can solve by integration or by solving differential equations, or eventually having to solve everything numerically. So if you see this kind of overarching arguments, you have the essence of this course. And the only thing which is going to change is actually the force. So when you have made the analysis of the physics problem, then you have the acceleration. And when you have the acceleration, you're ready to solve the equations, either analytically or numerically. So that's the main theme which we are going to, focus on during most parts of this course here. Now, what I want to do, if there are not any questions about this, and you've probably seen some of these cases before, I wanted to discuss a little bit the homeworks. So let's go back to the assignment which we have this week. And I wanted in particular to look at exercise 5 and 6. So unless you've done it, hopefully this can be of some help here. So this is the case of a puck, which is on a table, and there are two forces. So if you look at exercise 5, so we have two forces acting, and we need to set up a coordinate system. So we have the normal force, which acts, normal force, which now has a magnitude. And we simply set that one to n, with a magnitude n. So that's the value of it. And it's perpendicular. So perpendicular to the board. And then the other force, in this case, is gravity. And then we have gravity, and gravity G. And what we can do in this exercise, since we have, since we have an angle theta, we can actually split this one in two components. So we can have a component. So we are thinking of this gravity pointing downwards. So we can split that one into a component which is perpendicular to the board. Perpendicular to the board. And we would then perpendicular to the board and parallel down the board. So we would then write this one as a minus m times g times a cosine theta. And then we have the other component, which then is acting on the board, and the component minus mg times sine theta, which is now acting on the board itself. So we have no force across the board. Across the board. So if we now think of this system in the following way, so we would have a position R, the initial conditions, which is then defined by an object which is at rest, 0, 0, 0. So this is the x value, this is the y value, and this is the c value. And then we give it an initial velocity, v0. So this is r0. And we are going to call this a v0x. There is a v0y. And then we assume that there is no velocity in the z direction. So sometimes some of the exercises which you find in textbooks can be a little bit difficult to decode. So I hope this kind of decoding can help you in setting up the forces which are acting on the object. Now, if we now look at the x direction, so we have to define an axis system. So we would typically then define an axis system with x, c, and y. So we could have x and y, and define the board. And then we have z, which is the perpendicular axis, and you would have the gravitational force then pointing downwards here. So you can think of the gravitational force pointing downwards, minus g. And then we have a normal force which acts on the board, which is perpendicular to it, which is n. And then we would have the force in the x and the y direction. So when we dissect the problem here, if we look at the x direction, then we have zero acceleration, we have zero force, and that would be m times x second derivative. So remember that this symbol x double dots here is the same as the second derivative. So this is actually the acceleration in the x direction. If I look at the y direction, then what I'm going to have is minus mg times sine theta, because that will be the force which acts on the puck on the table. And this is going to be equal to m times y, second derivative, so which is the acceleration in the y direction. So this is the same as m times ay. And then finally, when we look at the z direction, what we would have then is the normal force, and I'm just setting up the magnitude because I've decomposed it in the z direction already. So n works only in the z direction, it's perpendicular to the board. And this is balanced by the gravitational force. And this is the same as m times the z, second derivative. And what we are assuming now is that there is no force in the c direction. So this is the way we would now decode the text in the exercise. Now, if we now look at these equations, if we start with the velocity in the x direction, or the acceleration in the x direction, what we would have then is simply now that the mx second derivative, which is the same as m times dvx of dt, is equal to 0. So this equation here, if we now look at the equation, we now can divide away the masses. The acceleration is equal to 0. So when we are integrating up the velocity, we have an initial velocity, v0x, And then we have the velocity in the x direction, which is simply given by this dv dx prime, which is equal to 0. So when we integrate this up, this simply means that the velocity is a constant in the x direction. And that sounds reasonable, right? Because we have no force in the x direction. So then the velocity has to be constant. So that means that we have v0 x. Now, we have assumed that this, from the initial values, is different from 0. And this is the assumptions which we made here when we put up the initial conditions. So the next thing is that now we can integrate up again, and we can find the position. So we know that dx dt is actually equal to v of x. And that means that we can integrate up as we did before. So this is one of the simplest way by which we can solve this equation, the first approach, as we mentioned. And this gives us x of t minus the initial position, x0. And if we now go back to the initial conditions, we see that we have put x0 equal to 0 here. So we can just put in 0. So that gives us x of t. And then we are just integrating up the velocity, which is v0x. So we're integrating from a time t0 to t, and then we have v0 of x of dt prime. So that means that the position in the x direction is simply v0x, the initial velocity, times t. And that's a pretty obvious result since we have a constant velocity. So I'm hoping I'm not offending you if I just state some of these statements, which some of you may think are trivial, and probably you have seen it in Physics 181. But we need this way of thinking and to simply get that drilled in and get it in our veins, because we are going to repeat these things again and again. The next thing we can do now, we can go to the y direction. And if you look at the y direction, we now have a acceleration, which is given by the gravitational constant times this angle sine theta. So if you look now at the y direction, what we have then is that m of y, which is the same as m of dvy dt, is given by m minus m times g times sine of theta. And then we just divide by m here. We don't need that. And then we can integrate up again. So what we would get then is that dvy is simply equal to minus g times sine theta. And then we integrate velocity on the right-hand side, no, left-hand side, and the time to perform the time integration on the right-hand side. And if we then perform the integration, what we would get then is v of y as a function of time minus the initial velocity, v of y0. And that's going to be equal simply to minus g, which is a constant, sine theta, which is a constant. And in the numerical exercise, you're going to put in a value for the angle theta. And this just has to be multiplied with time. So then we have the velocity in the y direction. And with the velocity in the y direction, we can then get the position in the y direction. So we just remind ourselves then that dy dt is equal to v of y. And we have the expression for v of y, which now is simply v0 of y, which is a constant of our initial velocity, minus g times sine theta times t. And then we can integrate again, new integration. And I'm just going to give you the results. I hope that's okay. New integration here. And what we get then is simply now a result which says that y of t is going to be equal to v0y times t minus 1/2, since we're integrating up here, times sine theta times t squared. And remember now that y0 was defined to be equal to 0. Now for the z directions, we have no force. We have an initial position, which is 0. And we have an initial velocity, which is 0. that means that it stays at rest in the z direction. So what this means is that z of t is simply going to be equal to the roundest number you can think of. So this is the solution of the equation. And then you can ask yourself, what is the time it would require to reach the floor? But let's now write up this final solution as a vector, r of t. And this is going to be equal to v0 of x times t. And then we would have a v0 of y times t minus g times sine of theta of t squared divided by 2 and 0. So that's the final expression for the position of this object, which is now moving on this board under the influence of a normal force and gravitation only. So this is one of the typical ways by which we now can use the first approach and integrate up with the right initial conditions and then find the final position of this object as a function of time. And this is essentially what mechanics is about, to figure out what is the dynamics of an object as a function of time. Now, then you can ask yourself, what is the position or what is the time it needs to return to the floor? And then clearly what you would say then is that when it returns to the floor, you would have a final time where you're simply setting y as a function of final time to be equal to 0. And in our case, that means that we have an expression where we simply need to solve a pretty simple expression here. So this will be final time, tf, and then I have a sine theta of tf squared divided by 2 here. And if I do the algebra properly, what I get then is that this final time, t of f, is equal to 2 times the initial velocity divided by g times sine of theta. So that's the final time. And then you can ask how much it travels till it reaches the floor in the x direction. And then it travels a distance which is now equal to x of t of f. And that would simply be v0 of x times this time, t of f, which then becomes simply 2 times v0 of x, v0 y, divided by g and sine theta. So this is the exercise, this exercise 5, and hopefully can be of some help. Now, the thing I wanted to say a little bit about now is how you could encode this. Because now we have an object which is a three-dimensional object, and that means that we would need to plot it, or plot this position. So if somebody asks you, what is the position of the object as a function of time, what we would need to plot then would be an object which is three-dimensional. So we're going to plot the position as a function of the x direction, the y direction, and the z direction. So this is the x component, this is the y component, and this is the z component, which is just 0 all the time. So we don't have any, sorry for that, this should be z. So in principle here, we could just plot the position using x and y only. Now, if you look at what we have here, there's something we need to pay a little bit attention to when we are dealing with Python programming. There are several ways by which we can do that. So Python ways of dealing with a problem. Ways of defining an object R, which depends on time. So it means that we have discretized time. So we have a discretized time here. And suppose now that we have t, which is given by 100 time steps. So we have a t0, the initial time, t1, up to t99. So we have 100 values here. And then this r, we have r of t depends now on x of t and y of t. So there's no problem in introducing the Z component. And I see that my time is running out. So let me just set up that point. So we could now define in Python, we could now define a matrix. In Python, we will then define R, which goes like R, and we will define that as an array with numpy. And if we want to initialize everything to zeros, we would then define this as something which now contains these 100 elements here. So 100, and we would have 2 here. That's one way to set up an array, or this actually becomes a 2-dimensional array, which again is translates into a matrix. So this could contain time, and this would contain X and Y. So you could let the first component refer to X, and the second component refer to Y. Now on Friday, when we do the exercises, what I'm going to do then is actually to sneak in just a few minutes where we look at the way we can set this up in Python. In 1 dimension, everything is simple. In 2 dimensions, we can actually use a very compact way to express this in Python. But it can be a little bit confusing in the beginning. But now I need to stop because I don't want to exceed over